So it is 9 o'clock now. So if we want to start on time, we'd be starting right about now.
Okay.
We have a few more people that I would imagine will join us, but if they want to go back, they can always watch the very beginning, and I want to be respectful of people's time.
All right, sounds good. Well, with that said, welcome everybody to today's webinar sponsored by the Create Energy Center. Today we'll be hearing from Saranya Gunasingh from Slipstream and Jenny Brinker from Northeast Wisconsin Technical College. And they will be presenting a really cool, it says a simplified energy modeling tool. And I think simple is true from a user's perspective, but it's really pretty powerful. I was introduced to this by Saranya and her colleague David at Slipstream, I guess about a month ago now, and I was so impressed. I thought this was something we should share with the rest of our community. Before I introduce the speakers, let me just say a few other things to put on your calendar and a few details for our presentation today. As you know, the Create Energy Center website is createenergy.org, and you can find announcements for all of our upcoming events, as well as a recording of this webinar today will be posted on our website after it is complete, along with audio transcripts for those that are interested. And if you'd like to mark your calendar for an upcoming event on Friday, May 6th, we will have one of our colleagues, Deb Hall from Valencia Community College, talking about building automation system tech Barbie, and to see her smart Barbie Grand Hotel in action. This has been a really cool activity that Deb's been working on for some time, and I know many of us are looking forward to that presentation coming up in the next couple weeks here. Before I introduce our speakers, let me also just say, please feel welcome to use the chat window to post questions. Gabby will be muting participants' mics while our speakers are presenting, and I will do my best to try and moderate and watch the chat box and then field questions for our speakers that they can entertain towards the end of the presentation. Our presenters today are Saranya Gunasingh and Jenny Brinker. Saranya is a senior researcher with Slipstream based out of Chicago, Illinois. She's an expert in energy analysis for designing high-performance buildings and in conducting field research of emerging building technologies and control systems. And we're thankful to have Saranya with us today. Jenny Brinker has been teaching about energy management technology at Northeast Wisconsin Technical College since 2015. And prior to that, she conducted hundreds of energy audits through working in consulting and utility customer service. And I'm also proud to say that if you go back far enough in Jenny's resume, she was an adjunct instructor with us here at Madison Area Technical College as well. So with that, I'm going to turn over control to our two speakers, and thank you both for joining us today.
Thank you, Ken. So I'll get started with our introduction to the simple energy modeling tool. And just give me a minute to share the screen here. Okay, let me know if you can see my screen.
We can. It's not in presenter mode. We see your whole, there you go. You got it.
Awesome. Yeah, thanks for having me, everyone, and thanks for taking time out of your Friday morning. Hopefully, we'll make your Friday a pleasant one with this presentation. So my name is Saranya Gunasingh. I'm a senior researcher at Slipstream. Slipstream is a nonprofit organization focused on accelerating climate solutions for everyone, and we do a lot of research, technical consulting work, education and training programs to work with a variety of stakeholders to advance energy efficiency in buildings. And the tool that we're going to present today, called Sketchbox, was a homegrown tool that we've been developing for almost a decade now. And the tool came into existence because, as you know, energy modeling tools are pretty complex. It can take hours to set up a model, and I have ran models that technically took a whole night or a whole day to run. And when you're doing a lot of volume of models, that's really not very possible to spend so much time building an energy model. And the other challenge is that when you have a building you want to analyze that, that doesn't exist, you have a new construction building we're just starting to talk about a new building, or you're talking about an existing building and you want to think about what are different ways to make this building more energy efficient. You really want to have tools that can do the analysis pretty quickly, that can analyze a few different options and tell us what's going on with the building fairly quickly, instead of spending like a week or 2 weeks setting up a model and running the analysis. So that's how Sketchbox came into play. We took the Do2 engine, which eQuest runs off of, and created a simple graphical user interface like the screen you see on your right side, which we will be demoing in a few minutes here, to make it really simple for the user to understand how energy modeling works, and gives us the flexibility to analyze a lot of different options in a very quick, in a few minutes time. And so we're not losing any of the robustness of the Do2 engine of the eQuest energy modeling software, but rather we're just making it easy on ourselves. A lot of the options are automated, so you don't have to go back to the building energy code and see what the code values are, spend a lot of time gathering those inputs and then transferring it to the energy model. A lot of those processes are automated, so you don't have to spend a lot of time on that. So this also, the other method we've employed to make this tool faster is that instead of like eQuest, where the simulation runs on your local desktop, this is hosted on the cloud. So we also make use of cloud computing. So multiple users can use this tool at the same time. And the computing time is very short compared to running eQuest on your desktop. It includes a lot of different building types. Anything you see in CBAX, we've pre-programmed it into this tool. So all you have to do is pick your location and pick where the building type, and you will be able to see a lot of the baseline model auto-populated. And additionally, we've also built in schedules and different mechanical systems. It can also do some advanced mechanical systems like ground source heat pumps, which eQuest has a little bit of a challenge if you're familiar with the tool. So we have a lot of different options that a user can use. It's also a super simple model. So if we're thinking about students who will be using this model, you can help this tool to talk about what is the physics of building science, like how does heat transfer from the exterior to the interior of the building? And when you change the characteristics of the building, like the building envelope, you change the number of windows, the orientation of the building, what does that mean for the energy use of the building? Like how does these physical, tactile characteristics of the building translate to how much kilowatt hours of electricity and terms of natural gas it uses? So what you see here is the results from a sample simulation that we did, and this tool will give you the analysis for different options. So compared to the baseline building, when you upgrade this building with energy efficiency measures, here is the savings in terms of the energy use intensity for each of these measures. And similarly, it also gives us the breakdown of energy end use. So we'll see when I do the demo, each of these bars correspond to a specific energy end use. The red bars are heating, the blue bars here are cooling. So we'll see that we have the distribution seasonally for heating and cooling. And how does changing the characteristics of the building impact the energy use? What happens, like how can you make the building more and more energy efficient, which also helps the students think about what are the basic thermodynamic principles that you're learning in like middle school physics. How does that translate to practical application in the field once they start their careers? We can run a number of parametric runs. You can set up like 20, 30 different parametric runs in parallel and compute the energy impact for each of those runs. And I'm excited to show this tool to you. With that, we'd love to support you with using this tool. This is free, so I just wanted to offer the tool to you to use and bring it to the students. Hopefully help them do a few exercises, walk around their buildings, analyze what are different energy efficiency measures that I can use in my home or in my classroom, in my school, they bring those ideas into this tool, and we'll see that this is a very simple tool for the students to use and help them understand opportunities to save energy. With that, I will pass it on to Jenny to introduce some thoughts she has for using this tool in the classroom.
Thank you, Saranya. And yeah, if you could just go back to slide 7, that would be great. I'm talking to you from Northeast Wisconsin Technical College and our Great Lakes Energy Education Center. And I have to say, I'm very excited to have a student online as well. Macy Herm will be talking about a project she has been working on as part of our Building Energy Simulation class, which is offered as a 3-credit course as part of the Energy Management Technology Associate's Degree program. I just heard yesterday that our program was approved as a Certified Energy Manager Provider College, so we're working on the paperwork for that, but I just wanted to put that out there. We're joining other colleges out there, so I guess I'm excited to be part of that. The class that we use building modeling in, including the work that Macy is doing with Sketchbox, is a class that looks at a variety of building energy modeling tools. So we have heavily relied on eQuest when we are doing our service learning activities for energy auditing. And when students reach that point, they're in their last semester of the associate's degree, and they have studied HVAC, lighting, and other, building energy use fundamentals. So when we enter information into these models, students, get to apply what they've learned, the acronyms that they've had to memorize, such as VAV, variable air volume, or what does the architectural term fenestration mean that they learned in blueprint reading, which is Windows. And I just want to let you know, besides Sketchbox and eQuest, we do take a look at DOE2, which Saranya mentioned is kind of the platform a lot of building modeling tools are built on, including Sketchbox and eQuest. And just yesterday, Macy and I were looking at RedScreen, which is a really great tool for providing, just like a database of cost information and other details. So if you're looking for tools to use that can estimate like new heating system costs, I think RedScreen out of Canada is a pretty cool tool. And then on the right, I have a graphic for Open Studio, which is another software that we kind of survey as part of this class. My email is included on here. If you'd like to contact me directly with any questions, I'd be happy to share. So I guess, Saranya, you're driving, so I'll ask you to go to the next slide, please. Thank you. This year, I'll just mention that we are working on a service learning project at our county zoo. It's the Northeast Wisconsin NEW Zoo, and particularly focusing on the Mayan restaurant there. This is a fantastic project in terms of conducting a high-level energy audit. Students need to analyze infrared imaging. We're doing data logging, and overall, just making sure that we can analyze all of the energy users. And when you consider what goes on in a restaurant, a building modeling tool is really great to help us understand interactions between equipment. So in buildings, you'll have lighting, which provide light, but they're also providing heat. In a restaurant like this, you obviously will have grills and fryers, which are contributing to the heat load as well. So there's really fast and easy way to do this is with building modeling to analyze those interactions of the heat loads and their impact on the overall HVAC system. So these pictures were from a cold day in February. I guess they don't have the peacocks warming themselves up by the compressors on the side of the building. But again, just a really great place for students to look at all kinds of energy consumption from buildings. And with that, I'm happy to pass the mic over to Macy. She's going to talk about the project she's been doing with Sketchbox and looking at parametrics. So Macy, thank you so much for being here.
Hi, Jenny. Thank you for having me. So we're currently diving into parametrics with the system. If you go to the next slide, please. So our strategy is to make the baseline the easiest. So like we're going to apply this to other schools and stuff. So like for them to kind of get into the system, it would be an easy way for them to see the difference in just like the slightest ways, like perchance the windows and stuff. So we would leave the baselines normal. We wouldn't adjust anything. And then if you go to the next slide, we would make like the slightest change, and we would want them to use like their geographical location. So they would have to put in like a frame of mind of where they are, what would be the most efficient logically, you'd think, you know, like for us, we would position our windows in the south for us to make our like sunlight and maximize like the use that we can, which would theoretically cut down like the kilowatt hours and stuff. But this is all like stuff that they would get into when they add like the parametrics. So like, I guess that's really all I have to say.
Yeah, thank you, Macy. Yeah, parametrics are an important part of the study. So I think that you putting together kind of a lesson that high schoolers could use is a really good way for everyone to, you know, take away, you know, how, like you mentioned, the windows facing south versus other orientations and how that parameter would impact the overall building energy use, as well as orientation, you know, which direction the building would face. So nice job on a professional development webinar, Macy, first year student. Thank you for being here. And it's back to you, Saranya. You can keep going with your good information and demo.
Yeah, thank you for that, Jenny and Macy. That it's really interesting to see the student use the tool. It's helpful for us to kind of keep going at developing the tool too. So with that, I will go on to a demo of the tool. So this is what the interface looks like. As you can see, it is hosted on my Chrome web page. You don't need any specialized software to run this tool. You can go ahead and get started with this project. So this goes through a few different building characteristics. First, you define what the project is, and then the design and schedule tells the tool what the baseline building looks like. It helps develop the baseline. And then finally, the last two tabs, the measures and the results.
Saranya, I don't mean to interrupt you. It's Gabby. We can see your screen. We're still back on the slides.
Oh, sorry.
That's okay.
Thanks for letting me know. Okay,
no worries. There you go.
Okay, perfect.
Yep, now we see the
Sorry.
demo. Thank you.
Sorry about that, everyone. Yeah, so here are the major tabs that we need to work through for this tool. So the first three tabs help tell the tool what the building looks like, define the basic parameters of the building, which helps the tool set up the baseline. And then the last two tabs, the measures and the results, helps us see what the results of the simulation are. So for the project, we'll go ahead and start setting up a sample office project. I am in Illinois, but we have all the US states programmed in here. So when you pick a location and the nearest city to where the building is located, that helps the tool pick the right weather file. So as you know, there's different climate zones in the US, and it's really important to make sure that we're doing the simulation for the location we have in mind. So I'm just gonna leave this at Chicago here since I'm here. And we also have a whole lot of base energy codes pre-populated in the tool. So in Illinois, the base energy code is IECC 2018. You could also go back to a 2015 code or one of the earlier codes if we're looking at an existing building which was built to be compliant with one of the previous code versions. We can absolutely do that. We also have some basic information about the cost of electricity and natural gas, as well as the tons of carbon dioxide that will be avoided if we made a more energy efficient building. The tool has pretty much every single value auto-populated, but if the user has better definitions, we can absolutely go ahead and put that in. So with that, we've set the basic location for the building, the fuel prices, and so on. Now we can go ahead and start building out the geometry. For those of you that are familiar with any of the eQuest offspring, the Do2 offspring like eQuest, you know that once you build a geometry, it's extremely difficult to go back and change it. You pretty much have to start the project from scratch. That is not a challenge anymore with the Ripple tool. So we can see that we started out with a medium office building that's about 3 floors big. We can go ahead and change that to 15 floors, make that a high rise. If we wanted that to be a bigger building, we can do that. So there's a lot of flexibility to change the basic parameters of the building. I'm just gonna leave this here and say that this is about 6 floors. You can say if it's a different building type, you can go ahead and change it. This is where all of the major CBEX building types are pre-populated in this list, and we can change the building type. Changing the building type, and as you can see, there's the orientation. This is very useful. This is one of the basic things a beginner user to energy modeling would have to understand. Like, what are the impacts of changing the building orientation? What's the impact of changing the window to wall ratio? We really don't want the west to have the most number of windows, so we can go ahead and change it to the lowest percentage. I just said set the west orientation to have about 20% versus the north. We really want the north light, so we can change the window to wall ratio on the north side to be much higher. So for someone that's really playing with the tool, trying to understand what are the different implications of changing building characteristics, these are really small but sizable exercises to understand when I change the window to wall ratio, what happened to the overall energy use. Now, what's the implication of a building being massed this way, which is just 2 floors, versus a building being massed with 10 floors. Now, the comparison between these two will help understand where is the majority of the heat loss going from. In this building, it's going to be the walls, because there's a lot more wall surface area than the roof. So here, to make this building more energy efficient, we want to focus all of our dollars getting the building envelope more energy efficient than we would put into the roof. Versus in a building that is designed this way, we really want to focus on the roof, because a lot of heat transfer is going to happen through the roof than through the walls. So these are like simple massing exercises, changing the orientation of the building to understand what will happen to a building as we build it. And like I mentioned, there's also a lot of pre-populated mechanical systems. So this can be varied to reflect the actual building, or if it's a new building, then we can go ahead and choose the most applicable mechanical system type. Then again, with the schedules, we have some schedules. The other thing we can do is if we wanted to add another building, like we can add another one. So let's say that this is a parking garage, then we can definitely don't want the parking garage to be bigger than the building. So we can go ahead and define where this is going to be. So you can attach it to a different surface. So you can attach the parking garage to this surface, so you can move it under, over. So again, changing the orientation of the parking garage, how is that going to impact the energy use of the building? So we can go ahead and define some schedules for the building. This is pre-populated. As you can see, for the office, the people come in around, the occupants come in around like 6, 7 a.m. That's when the building starts being cooled and heated, and all of the internal use profiles follow the occupancy. Like the occupants come in, that's when we need domestic hot water, we need the maximum lighting, and the miscellaneous plug loads also are peak during that hour versus during the non-occupied hours. We will see that the parking garage schedules are a little different because it really doesn't have much ventilation, domestic hot water, or like major loads associated with it. What we really have is a lighting that's going to be fairly constant. And again, if we wanted to change this, if we think that the office is going to be occupied for more hours, then we can absolutely go ahead and change that. So if we want it to be like occupied at 5 a.m. and it's going to be occupied till 8 p.m., then we know that we can just, by the drag drop of the slide bar, we can change all of these schedules. With that, we pretty much had the baseline model all set. Like Macy pointed out, once we have a baseline model, that's just a code compliant building. So we're not going to go change much of the baseline input. This is really telling the model what's the legally allowed building that can be built. Anything lower than this is technically not legally possible, although that does happen, unfortunately. We can then think about what are the different kinds of energy efficiency measures we can apply to this building. Can we make the building envelope more energy efficient? How about the window properties of glass, the U value, solar heat gain? So you can either add a measure, or the other thing that we have programmed into this tool is adding a measure set. So we see that we created 2 shells. One was an office, one was a parking garage, and you can add a measure set. This brings in a lot of standard energy efficiency measures applicable to these 2 building types. And a lot of these numbers might to a beginner seem a little overwhelming. So what's been done in this tool is that there's 3 columns, as you see. The first column is no change, which is the exact same value as the baseline model. The second column is a little better than the baseline values. So this makes the building a little bit more energy efficient, but not quite the best possible building we see in the market. And then finally, the best option gives us that if you really push the envelope of building performance, where can we get this building to be? Like, how much more efficient can this building be? And finally, there's the user can override any of these values. It doesn't have to be the better or the best. You can absolutely go ahead and set a value here. So for example, in this building, the purple ones are the parking garage and the gray ones are the office building. So let's say we really want to put in very good glass for the office building, then you can go ahead and change that to 0.27. This is the U value. And for the solar heat gain coefficient, again, let's do a 0.7. You can set the custom value. We can look at the lighting. Like Jenny pointed out, there are buildings where the lighting or the internal equipment load is going to be very high. If this were a kitchen, we can change the interior equipment watts per square foot, the equipment power density to be pretty high. Let's say, again, we're doing all LEDs in this building. We want it to have very efficient lighting and so on. We have quite a lot of options pre-populated here. Additionally, you can still add a measure, like let's say orientation. So we can change the building orientation to see how that's going to impact the I'll just add one. Can add measure. So let's say we're going to change this building at 90 degrees. So turn this building around in its site by 90 degrees to change the orientation of the long axis of the building and see how that performs. Now, this will take a couple minutes to run. I already ran the model, so we can see the results while my other tab is pulling the results together. So once the simulation is complete, here's what we will see. Here's a very high-level summary of what happened between the baseline building and the measures that we added to make this building more energy efficient. We get some very good data on what's the total energy cost and the savings. So this building saves about $20,000 in utility cost annually. how much electricity and natural gas we save, the energy use intensity, both the site and the source, as well as the CO2 of carbon emissions that we've avoided, which is becoming more and more important for a lot of customers to know what their CO2 emissions are. And if the school district has a specific sustainability goal in mind, this can be used to decide on, if you make improvements to the school buildings, then how much CO2 can be avoided there. So the simulation is complete. And then we also see a breakdown of energy end use. We added a lot of measures to this demo, so cannot really pinpoint any of these reductions to specific measures. But if someone just did a lighting retrofit, then you can just go ahead and see the energy cost reduction. And you know that a lot of that is because of the more efficient lighting design. We also see how that plays out seasonally. We see that in the baseline, the red bars are much bigger, meaning there's a lot more heating demand, versus in our actual design condition, the red bars are much smaller. Similarly for the cooling too. So that's where the savings came from. A majority of heating and cooling has been eliminated. And then again, if you recall in the measure set, we did all LEDs. We changed the lighting power density from a 0.7 watts per square foot baseline to 0.3. So you see that reflected in the yellow bars here. The yellow bars are much smaller in magnitude in our design condition versus in the baseline case. And this is also an opportunity, like if we did just the lighting, this is an opportunity to talk about energy interactions, like Jenny pointed out. Like what we would see is that the lights also emit a bunch of heat into the space. So while we see the lighting go down, we will see the heating kick up a notch, because the mechanical system is going to try to make up for the heat that was eliminated from the space. Overall, we'll still see a positive impact on energy use, because the lighting reduction is much higher than the heat that was emitted into the space, especially if we're talking about LEDs, which don't, compared to the compact fluorescents, they don't put in so much heat into the space. So these are all like really good opportunities to review a whole lot of different options of thermodynamic interactions in the building, and see how you can make your building, the space, a lot more energy efficient. And the final tab we have here is about the different individual measures, and see which ones make the most positive impact. The orientation was not a good choice, because we're seeing a negative energy cost savings. So turning the building around 90 degrees was not a good option. We can go back to our parametric analysis page and see if we can change this to a different axis, or leave it like it was initially. But a lot of the other measures have a positive impact on the energy cost, especially the interior lighting, because we did very efficient interior lighting that has the highest impact on the dollar amount we spend on utility bills a year. So this is pretty quick high-level overview of what this tool can do. Again, going back to the measures, deleting or adding more measures is pretty simple, and then you can rerun these results in a matter of a couple of minutes, if that. Now I can take any questions if anyone has questions, or if you'd like me to demo a couple different options.
I'm not sure if all the participants have unmuted their mics, but feel welcome to either ask questions or type them in the chat box. I can speak for myself, Saranya. I'd certainly be interested to see some other examples too. We do have probably a good 20 minutes or so left for Q&A and discussion. One thing that I am kind of curious about, maybe I see Saranya's queuing up maybe another example there. I am curious to hear some ideas about how this tool might be used by teachers in the classroom, and this is probably a question more for Jenny. And any ideas about possible lessons that could be developed for using this with students?
Yeah, I'd be happy to address this, and Saranya, please add. And I should also say that it's been really nice to work with Saranya and Slipstream, when they kind of were developing this tool. They asked me to try it out with some of my students. So that's been really nice to kind of be part of this process. And, what we could do, Ken, as like a one-day exercise, one classroom exercise, which I've done with high school students, not with Sketchbox, but an idea, is that you could start with a basic building, and Sketchbox offers you a selection. You saw Saranya kind of go through the demonstration, and when you are under the design part of the tool, you can choose perhaps a school building, and what you could do as one day or one, class kind of activity, you'd have to do some prep, is just ask the students to compete. What can you do to keep that school building maybe the same size? Keep a few things the same, but then from there, kind of have a competition as to, what can you do to make your design the most efficient? And you might have to set that up with some examples, but overall, when I've done that with a different software with high school students, if you just give them, some basic parameters and then a goal to reach, and that might have to include defining some energy terms depending on their knowledge base, you can, guide them to a competition on designing the most efficient building.
So,
Any other ideas?
That has me really curious, a sort of follow-up to that, Jenny. And I'm seeing some stuff come across the chat box now about folks that are interested in how you might do this with a group of students. And having not used the software myself, I'm curious, Saranya, is it possible to set up the base case with a building like say a school? If you know the basic parameters for your school, how many square feet it is, how many stories it is, and then give all the students a base building that would represent their school, and then let them sort of tweak it and make modifications and do like Jenny suggested, have a competition to see who could come up with the most improvements or the most cost-effective strategy to improve that.
Absolutely, yeah. That would be a great, exciting exercise for the students to do. So if we wanted to do something like that, what we would do is change the building type, or you can start off with a new project. Say it's a school university, so a lot of the schedules and inputs would reflect more closely for school building. If there's a couple different buildings, I think that was the question that we got in the chat box about different construction properties. Could you model the building as multiple adjacent buildings? Yes, absolutely. Yes, that would be the right way to do it. If there was a different shell, what you can do is add another shell. So if it's attached to this building, you can move it like we just did with the parking garage, or if it's disconnected, we can leave it be and assign the most appropriate energy code for that particular building. Unfortunately, here, the baseline code will apply to the whole project that we're setting up here. But if there is a significant chunk of the building that was, built 30 years later, then you could set that up as a new project. And like I'm doing here, you can, this is a completely different project that I ran this morning to just make sure that everything was working fine. So you could set up this project with a different energy code. Like, let's say this is a really old building, so I'm going to set this up to 2006 code. And then this is going to be the newer edition for the project. Alternatively, the other thing you can do is once you have the building shell selected, you can change the baseline input. So what really the code impacts is the baseline inputs. The roof and the wall ULUs might be a little bit inefficient compared to our 2018 energy code. So if you have a better data on that, what the wall construction was, if it has no insulation, if it's just like about 9 inches of a brick wall, then you can calculate the ULU and then manually put this in here. Similarly, if it's a single pane window and you know that the ULU is not as efficient as this, you can do that here. If we know that there's a cafeteria in this building, we know that the equipment power is going to be pretty high. There's probably a commercial sized kitchen, then the equipment watts per square foot is going to be a lot higher compared to if it's a classroom. So we can go ahead and set up individual inputs like that. So that, let's say this is pertinent to the school, and then there's another building that is reflective of the office spaces in the campus, and then there's a parking garage. If we needed more building types and end uses, we can absolutely add that here. If say there's also opportunity to add a lighting control, if there are daylight sensors in the building, then you can mention that there is a lighting control here. And that impacts what percentage of the lighting fixtures are controlled by a daylight sensor or an occupancy sensor versus other parts of the building that may not have a lighting sensor attached to it. Now, if we go and run the model, it's going to have 3 different tabs as opposed to the 2 that we saw here. Oh, this is updating results too. Yeah, it should be here in a couple minutes, but we'll see that there's 3 different line items for the office, parking garage, and the school spaces that we set up in this model. So for a student that would be doing this as an exercise, walking around, I would say that the envelope inputs are kind of harder to look at, because once the wall has been constructed, unless there is an exposed wall somewhere, it's not really easy to see what type of insulation is inside the wall, how many inches of insulation are there, which makes it a little bit more complicated to calculate the U values. The best bet in that case might be looking at the drawings, if they have access to the original set of drawings, and then pulling out the building envelope factors from the original specifications. And, you know, it might have degraded a little bit over the course of 40, 50 years. So like set back these values to be more reflective of where the building is currently at. The really practical input, some of the practical things that the students could do would be to walk around the building, see what kind of lighting fixtures there are. Are there parts of the building that have been retrofitted with LEDs? So we have CFLs and T8s or T12s. Then calculating the lighting power density is a really interesting exercise that we teach a lot of our interns when we do field work too. So going around the space, calculating the number of fixtures, looking at the watt per fixture, so that you have the total watts multiplied by the number of fixtures, and then you calculate the watts per square foot based on what area of the building is lit. And then thinking about if it is an older lighting fixture, what would a LED retrofit do to the space? Because if a CFL is about 60 watts, the LED is going to be about 5 watts, if that. So what would that mean if 100 CFLs are replaced with 100 LEDs? What's the energy impact of that? So that's something that they can visually assess and bring it back to the tool and do the computations. Similarly, another thing that can be visually assessed is the mechanical system. There's typically a nameplate on our rooftop units, or if there is a terminal AC or heat pump. So looking up those nameplates to see what the efficiency is. Mostly we have the COP and EER, so this is the DOAS cooling efficiency, but here we have the cooling equipment efficiency and the heating equipment efficiency. So having these values updated based on what they visually observe on field, and coming back, looking up some manufacturer specs to see, is that really the most efficient equipment that we have? Also thinking about the economics of energy efficiency improvements. If it's a newer equipment that was retrofitted 5 years ago, pulling that out and putting in a more efficient equipment would not make the most sense, because these are expensive pieces of equipment, right? So also thinking about making a long-term strategy about, I see that the lighting is really old and that makes sense to retrofit right now, but mechanical system is only 5 years old and the predicted life of that equipment is probably 10 more years. So I suggest doing an evaluation of this building and then putting in the most efficient mechanical system, but at the same time running some of these simulations to see, if you do that, here's how much you will save in electric costs per year. So presenting that to the school to help the school prioritize the energy efficiency measures. If you have a facility staff on site, then having the facility staff come and weigh in with the students to help them understand what is their problem, like what are they seeing? Are there hot calls and cold calls? Do they get that a lot? Which means there is something not quite right with the mechanical system. So can we change that by changing the set points in the building? So again, changing the set points and the setbacks. If the building is not occupied at night, are we doing setbacks during the unoccupied periods? Because that can save a lot of energy. And unfortunately, we don't have a lot of buildings without a setback. So just making sure that we have a facility staff weigh in, ask them about what are the issues that they're dealing with on a day-to-day basis, and making sure that we address a lot of their concerns would be like a really practical exercise for the students to work on.
Just a couple of notes here that have come across the chat. And if folks are interested in adding questions but don't want to post them to everyone, feel welcome to send them to myself or Gabrielle, and we'll field them also. If you have your chat window open, Dave from Slipstream did post the link there to access Sketchbox. So you might want to copy and save that or open it up on a browser so that you have it handy. And Jenny did note that a big benefit of this tool is that it's based on an internet browser, so you don't have to download software and install it on workstations in a computer lab. And students, if you're teaching online or in hybrid mode, can access it from home, which I do think is a huge advantage for many of our instructors. So Saranya, you kind of alluded to this, and maybe I'll just ask the follow-up question. You know, for many schools, they might be 50 or 75 years old, or maybe even older than that. Is there any way within the tool to account for, you know, degradation to materials that might have occurred since the original construction, say, you know, insulation that's been compromised on the roof due to water penetration or something like that? Or is it just a manual tweak that we make, or is there some sort of setting that adjusts for that sort of aging factor?
Yeah, that's a great question. Unfortunately, we don't have any built-in technical, how do we call it, the process to adjust for those degradations. That would have to be a manual adjustment. And a lot of the times we have not put in those values in because that's going to be a little bit more specific to the vintage of the building and the kind of degradation we're talking about, right? So the tool does not automate that process, but that's absolutely something that has to be accounted for when we're talking about existing buildings that are, say, over 20 years old.
So that might be a good exercise for teachers to think about as well, as, you know, have the students model the baseline, assuming that the building is in the same condition as when it was originally constructed, and then go in and modify the various parameters in there and you know, adjust them downward to account for that aging and deferred maintenance, especially if they know there's places where there's like leaks in the roof or cold air that's making its way through window seals. I'm just looking at the chat over here. There was a question about, does the tool work for residential structures, or maybe is there a similar tool for residential structures?
We have multifamily built in. We don't have single family residential yet. But that is absolutely something we can think about adding. It depends on the number of people that have a need for residential modeling. If you are specifically interested in residential simple energy modeling tools, I would recommend looking into ResNet, R-E-S-N-E-T. So ResNet does some simple modeling for residential structures, and it has built-in residential energy codes to look at single family housing or like attached housing less than 3 floors tall. The energy codes that we have built into this tool are applicable to multifamily, 3 floors and up, as well as any kind of commercial buildings that that are included in the CBEX database.
And another question of just a sort of basic one about the tool. In terms of heating and cooling for buildings, is it possible to model a school that might be equipped with a geothermal system?
Yes, absolutely. Yeah, we do have a geothermal system built in. Let me see how to get out of this PowerPoint real quick and really quickly pull up a geothermal system. So that would be here on the airside system. So you can, sorry, here, the cooling system would be, you'd have to set the fuel to be all electric, and then be water cooled. I'm not sure where I missed that. Yeah, we have a geothermal system built in here. I'm just having a little bit of difficulty pulling it up. Or maybe I did one of my previous options might have negated some of these inputs.
Might have to start over from scratch in order to get that. Yeah. But that's good to know that it's in there, because I know that's becoming much more common with a lot of newer schools that are being constructed, that they're being built with geothermal. Just fielding through the chat box to see if there's any other. Oh, there was a question going back a little bit there. What is the difference between cooling and heat rejection? I think you spoke about that earlier on in your presentation, and that might just be helpful to clarify.
So I think there's only what we can do is look at heat rejection. But there's not so we can do energy recovery ventilators. The only way, if we're talking about ERVs, is looking at the ventilation and setting up an energy recovery ventilator. Then it asks you for the type of ERV, and we can set up ERV effectiveness. Is that what we're talking about? Is there a different input that I may have mentioned?
I'm not sure for the person that asked the question, but it is good to see that the ERV settings are there. That definitely makes sense. Let's see here. So another question, and this might be for Jenny. If you were a teacher, say high school or community college teacher, interested in starting to model their building, what's the best way to start or approach this with a class? Do we have any type of like a base lesson or introductory lesson? Or Jenny, do you have any suggestions for how you might use this tool with your own students?
There are some good resources I'd be happy to share. I'd have to kind of look them up about the basics of building energy modeling, because you can probably tell there's a lot of lingo that gets thrown around, right? So a big barrier would be to start with sort of a resource that can, you can find terms in order to understand what you're entering. And I believe that Sketchbox is working on some tutorials too, where you can kind of scroll over the inputs and get a little bit more information. And then you had asked about like, what would be the best way to model your particular building? Well, I'm sitting next to a pile of blueprints right now for that Mayan restaurant. The first step would be to get a hold of the building prints, and that way you have the ability to get the square footage, and you'd have to calculate the R value. So this is an awesome project. If you're going to model your building, you'd have to take some time to either work on it with your students side by side, or set it up and find a lot of those variables on your own. Does that help?
I'm gonna give a little plug for your Smart Start to Energy grant, Jenny. For those that aren't familiar, Jenny Brinker has a National Science Foundation project she's been working on with a high school instructor, Scott Litticoat from Green Bay. And they produced a really nice video that walks students through what a commercial building heating, ventilation, and air conditioning system is like, looking at all the components and how it operates. And I think that would be a really good first place to start, because most high school students have no idea how their building is heated and cooled. And it's completely different than the furnace that sits in their basement on a forced air system. So I think that would be a good first place to start, just to get familiar with the sort of mechanicals that operate in a building. And then also I would suggest reaching out to your building facilities manager and see if they would give the students just a walkthrough through the school. So to look at the HVAC systems, look at the building envelope, and get a little bit better appreciation for just how the building is constructed, so that once they get into the Slipstream software, they have an idea what all these various settings are in the model. And Greg is asking, is there a link to that video? And Jenny, I'm sure you probably can find that faster than I can. I believe we actually have a link to it on the Create Energy Center website, which is just createenergy.org. And Jenny, you probably have a link on the Smart Start page as well.
You know what, Ken? We don't have like a YouTube link for that one just yet. So thanks for reminding me that there is the HVAC lesson already posted on the Create website. Otherwise, I'd be happy to supply the MP4. It just hasn't gotten put up onto YouTube just yet. And thanks for plugging that Smart Start to Building Automation Systems and Energy Management project, Ken.
Yeah, well, you guys are doing some excellent work, and we'll be sure to send that out to the Create list as more of that work gets completed and is available for teachers to use.
We're working hard on it. Thanks.
Well, we are just about at the end of our time here today. I want to thank everybody for attending, and thank both Saranya and Jenny and your student as well for joining us and presenting. That was really excellent. We're so glad to been able to share this work with the rest of the Create Network, and we'll look forward to maybe doing another one of these series in the future when we have a few more examples of people using it in the classroom. And with that, I think we can conclude for the day. Wish everybody a good weekend, and we hope to see you on a future Create Energy presentation. Watch for us coming up in May on the Energy Hotel with the Building Automation System Barbie.
Thank you, everyone.
Thanks, everyone.
Thank you.
Thank you. Have a great weekend. Thank you. Bye-bye.